And here we go. Time for the love algorithm, which is a nice clickbaity title for what's been classically known as the secretary problem. And oh boy, it's way too loud in the next room. Hang on. My biggest fan. All right, so let's skedaddle over to this here. Let's see, where are we? Hang on here. Other things are popping up. It's doing bad things. Oh, I don't know. Okay. Oh, hello, Beryl. Thank you for showing up. I haven't started yet. I'm dealing with my technical stuff. Let's see. Share the screen. I'm just about to start. I can hear myself in the next room. Okay. Chrome tab. Okay. Okay, here we go. Okay, so the secretary problem. It's your classical. I don't know if you call it game theory. It's an optimization thing. But you put it down as the love algorithm because the idea is that you have a certain number of candidates for some single thing that you want. Okay, so maybe you decide that you want to get married in the next 48 months, and so and everybody that you date, you get to decide. You have to either decide or not marry them. I don't know why it would work that way. Almost a more realistic idea is, let's say that you are, and actually this is how we'll present it. Okay, let's say that you are at a car auction. Okay, and there's a certain number of cars. I'm going to say 19 for this. Okay, and what happens is you see the car for the first time when they're parading it. They drive it around, and you have to decide based on some sort of objective criteria that you have. You have to decide based on some sort of objective criteria that you have for ranking cars or ranking future spouses or whatever. How this particular car ranks on your scale. Okay, so if you had the opportunity, and we're going to use the number 19, if you had the opportunity to look at all 19 of them, you would be able to, because you've got some checklist, you would be able to decide which is your favorite, which is your next favorite, da 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 da. Okay, but you don't have that opportunity. You only see them one at a time, and then you have to decide at that time whether you're going to bid on it and buy it, or whether you're going to let it pass and go on to the next one. So you don't really know what you're up against. You see the first car and it looks okay and you could live with it, but how do you know what the other, chances are it's not as, there's other cars that are nicer and there's other cars that are worse. You don't know whether you're looking at the best of the lot or the worst of the lot. In fact, we're dealing with 19 cars, right? Okay, so 19 cars, what is the probability that the first car that drives by is the one that you would think is the best? Okay, so what do you got? Probability of the best? It's going to be 1 in 19. In fact, any given vehicle just pulled out of a hat, there's a 1 in 19 chance that it's going to be the best, right? So do you pick the first one, or do you look at 18 and then pick the last one? I mean, those seem like those are not optimal strategies. The idea is that you'll look at a sample to get an idea, because they're randomly displayed. Okay, so you're going to look at a sample to get an idea of what you've got. And then after that, you will decide based on the ones that you've already seen. Okay, so we've got 19 cars or 19 prospective spouses that you're going to marry. I don't know what it is. Okay, but I mean, this is, people have talked about this in respect to getting married, right? They go, I will spend a certain amount of time just dating and not even considering them, and then I'll marry the first person that comes along that's better than all the other ones. Here's what the idea is. So we've got 19 cars. I'm just going to do cars because it doesn't sound quite as cold. Okay, so we've got 19 cars, and we are going to sample some of them. Okay, so let's say we're going to sample 9 cars, and all we're going to do is look at them, and we've got a checklist, so we can decide among those 19 cars which ones we like the best. Okay, and then among the next 10 cars, okay, we will choose the first car that is better than any of the previous ones. Okay, so what we're after is, I chose this number as a matter of convenience. We're after is, what is the optimal sample size that will maximize the probability that we will get our personal best, our favorite car among them all. Okay, so in this case, we're going to work through this. We're going to sample 9 cars. We're going to talk about the probability, and then we will figure out how to make this number the best it can be, and then we'll generalize it for N cars or N spouses or what have you. Okay, so are you with me? Any questions? I can hear myself in the other room. All right, here we go. Okay, so you're going to check the first 9 cars. Okay, and you're just going to check them. You are not going to choose from among them. So now in this position, if that is the best car, given that that is the best car among them all, what is the probability that you will choose it and choose the best car? Well, if it's the best car among them all, it's going to be better than any of the 9, and that's the thing. It has to be better than any of the previous ones. So your probability is going to be 1 in 19. It's just the odds that it's the best car. Okay. Now, for this one, this is where it gets fun. Okay, for this one, if it's the best car, what are the odds of choosing it? Well, you would have to reject all of these previous 10 cars. So in particular, this car would have to not be the best of all of these 10. Okay. Yeah, you'd have to get to this one. If this one was the best, you'd have to get to it to pick it. Okay. So we have to presume that in this case, you would have to pass up this car. So the odds are pretty good that it's not the best among those 10. So what are we doing? We have 2 conditions that must both be met. Okay. This car must be the best, and this car cannot have been the best among the previous 9. So we multiply those 2 conditions. Okay. And actually what's going to happen is we're going to end up adding these individual probabilities. So let's go on to the next one. Okay. Let's say that this is the best car. Chances are 1 in 19 of that. And you would have to reject this car and this car. So this number 10 would have to be not as good as the previous ones. And this number 11 would have to be not as good as the previous ones. Okay? But what if you're here? And I think you see where this is going. Okay? What if the best car is here? Well, the odds of that are 1 in 19. And all of these would have to be rejects. So all the conditions from previous, plus the one just before it would have to be a reject. So that's over 11/12. And then add that, and then you're going to keep on doing this. Okay? And then finally, you're at the last car. What if the last car is the best one? Okay, well, chances are of that is 1 in 19, but you would have to reject all of these. 9 tenths times 10 elevenths times 11 twelfths, all the way up to 17 18ths, because this would have to be no better than any of these. Okay, and so the odds of that are pretty good. Okay, that it's not the best. So now we're going to sum up all of these things here. And there are some patterns that we can follow to simplify this tremendously. Alrighty, Beryl, you're with me. Thanks. Okay, so I got to factor out this 1 out of 19. Okay, and then we get all of this. Now, how are we going to deal with all of this? Well, the good news is that we have got you see here that we can do a lot of canceling. And what about this one? That. I think I repeated the same thing. And then finally down to here. So what you're going to end up with is this 9 is always going to be on top, which is 9. That's the number that we had originally decided to set aside. And the number that's going to end up on the bottom is this 17 is going to cancel with a 17 down here. I think you realize that. So the number that's going to end up down here is 1 fewer than our total number. Okay, and that's it. But of course, we're going to we're going to have to. That 17 doesn't. Just a second here, I messed up here. We're going to start with we're going to have 9. This number down here, these are all canceling. So just a second, these are canceling. Oh yeah. That's still there here. So we've got okay. So we're going to start with 9 tenths plus 9 elevenths plus 9 twelfths plus 9 13ths. And you know what? We're actually going to we have to consider this one. We factored out the 1 out of 19. So we're going to treat that as, instead of just putting 1 there, we're going to call that 9 ninths. It's going to make things work out better. So we go plus 9 17ths plus 9 18ths. Okay, and so we sum up all of these little fractions. But first, before we do that, we can clean this up a little bit more. We're going to factor out this 9. So we've got 9 out of 19 here. Okay, and so we've got 1 out of 9 plus 1 out of 10 plus et cetera, plus 1 out of 17 plus 1 out of 18. Okay, capiche? We're good? Any questions? We'll move on. All right, so you'll notice here, I mean, if we want to call K our sample size, okay, then this number here, that's always going to be K, and we're always going to start with K here. And this is going to be K plus 1, et cetera, all the way up to, and then if this is the total number that we have to choose from, we want to call that N, this number here is always going to be N minus 1. Okay, so now let's go and let's sum this up and see what kind of odds we're looking at here. Okay, so you're going to need to see what I'm doing. Stop screen. Hi, it's me. Okay, and share screen. We're gonna show off the show off Desmos here. Okay, so here's Desmos. So we'll sum this up nicely here. So we've got 1. Now I got to take a look at what I had. 9 out of 19 here. 9 out of 19. Okay, times the sum from, what are we going from? I got to go back and forth and look at this. Oh, okay. From 9 to 18. Is that right? Yeah, from 9 to 18. From 9 to 18 of 1 over N. So I've just put it all nicely here. And so what do we got here? We've got our odds here are 0.368 of choosing the best of the 19 by doing that method. Okay, but what if we had chosen, say, let's sample the first 10? So we're going to put that there and this here. Okay, that's a little bit not as good. The odds are about 35% that we're going to choose the best one. Okay, what if we decide, okay, I just want to take a look at the first 3? So we got to put 3 down here and 3 here. Okay, it's about 1/3 odds. Okay, but what was better? What was better was the 10, wasn't it? That seems to be the best so far of the ones that we're just mindlessly sampling. Okay, hang on here. How did the 10 end up there? Now it's 35%. Okay, I think I had 9 before, didn't I? There's our 9. Okay, so you know what? You can go to Desmos and you can play around with this. And if you play around with this in this manner, just by check, try it out and check it, guess and check, you're going to come up with the best number. But of course, we want to find a way to do this for any number N. Like, what if this number down here was 100? Okay. But if we had 100 cars to choose from, or 100 potential spouses, and so then if this was 9 here, we'd have like a 7%. Oh, that's got to be 100 though. Sorry, that's got to be 99. Okay, so we'd have a 22% chance. And if this was 50, we decide we're going to check about half of them. We've got a 35% chance. So we're going to optimize this baby. Hello, Gabixi. I hope you know where we're coming from, and you can play this back when we're done. If not, okay. So let's roll. Okay, so I've got to share with you my whiteboard again. So hang on. Stop screen and share again. That'll work with me. I'm old. Okay. Chrome tab, whiteboard. All right. So what a mess. Okay. So let's go back here. So we want to generalize now to this being K. Our sample size is K, and are the things that we're sampling, whether it be cars or dates or I don't know, or universities that you want to apply for, whatever. I mean, I don't know if people actually use this because it's so cold and methodical, and yet the idea is you've got to have some sort of objective way of ranking your prospective candidates, and you can't go back, right? So let's see what our general thing here is. So what we've got is I'll write this down again. Yes, I love Myro. We've got K over N, and we have it's a partial sum of the harmonic series is what we have here. Okay, K plus 1. I'm going to write this out a little nicer because this is what we're going to have to work with. K plus 2 plus ... plus, and then our final number is actually going to be just one short of N, okay? N minus 1. And we have a nice bit more of a formal way of rendering that, hey? Okay. Sigma little n equals K to big N minus 1 of 1 over N. Okay, so how do we optimize this function? And we are going to take advantage of another little fact here, which works better for large N, but it's a way of approximating this partial sum of a harmonic series. I don't know if you know the harmonic series, eh? Harmonic series. That's what this is, the sum of the reciprocals of the integers, okay? And by partial sum, I mean instead of just starting with 1 and doing 1 plus a half plus a third plus a quarter, we're starting in the middle someplace, and we're only going to sum, it's finite. Because if you sum the harmonic series, like 1 plus a half plus a third on ad infinitum, it diverges. Okay, but a partial sum, of course, isn't going to diverge. So we're going to take advantage of this very cool fact. Okay, this is a wonderfully accurate graph of that's y and that's x, and this is y equals 1 over x. Okay, and so let's suppose, and this is going to be all out here, but let's suppose that this is 1, okay, and so that's going to be 1, and this is 2, okay, so this is going to be a half, and this is 3, so that's going to be a third, and this is 4, So this little smidgen in here is going to be, actually, that's going to be a quarter. So summing the series, say from 1 to 1/4, it's going to be the areas of these rectangles. Okay, that's the partial sum of that harmonic series. Okay, but what is the area under the 1 minus, or the 1 over x curve? Okay, the area under the 1 over x curve, 1 over x curve dx is the integral from wherever we want to start. So let's just say we want to do the let's say we just want to estimate these two, these three, the 4, the 3, and the 2. So we want to estimate 1/2 plus 1/3 plus 1/4. Okay. What we can do is we can work out this integral between 4. Oops, I should put the 4 up here. Between the 4 and the 1. Okay. And that will give us the area under the curve, which is going to be a little bit more. It's going to be a little bit of overshoot. But what is that? That ends up being the natural log of x. Okay, that ends up being the natural log of x evaluated between 4 and 1. So that's going to be the log of 4 minus the log of 1, which is going to be log of 4 over 1. So in other words, log of 4. And let's check that out. Are you all with me? Anything I need to redo? Because when I'm talking to myself, I hear myself, and I get it because it works fine in my head, but maybe there's something I didn't say. So let's go over and let's look at hang on here, I got things happening. Let's look at Decimus again. Okay, share, stop screen, share, Chrome tab, Decimus, share. Okay, we're sharing Decimus. Can you see that? Yeah, okay, good. Okay, so I got to get rid of all this. So what did we estimate? We estimate 1/2 plus 1/3 plus 1/4. Let's see how close that is. So we've got the natural log of 4, and yeah, yeah, not so good, not so good. Okay, but imagine that we've got let's see, the sum from, I don't know, let's just do the sum from 10 to 100, 1 over n. Okay, so what did we say that was? Let's go back and let's look at this. Let's look at this StreamYard. Share, stop screen, share screen, Chrome tab. Yeah. Okay. So kind of what's our thing here? We're adding up 1/2, 1/3, 1/4, and what do we have here? So we've got the log of 4 minus the log of 1. So let's say then generally we've got n equals, well, we're going to try n equals 10 to 100, okay? So that looks like that's going to be, so this would be 10 would be the lower end and 100 would be the upper end. So we'd have the log of 100, because that's the 4, divided by, and it looks like what we've got here is not 10, but 10 minus 1, because it's 1 less than that 2 there. So divided by 9. Okay, so let's see what we'd end up with. And bring you up again. Share screen, Chrome tab, Dismiss. Okay, so instead of this, let's do the log of, what was it, 100 over 9, and there you get. See, you get a close enough approximation. Okay, so we're going to go with the logarithm here. And hang on here, I got notes that I was hoping to use and I'm not using them. Oh, there it is. There it is. Quarter, a half. Okay. Okay, so back to the notes, back to these. Share, stop screen, back and forth, back and forth. Share screen, Chrome tab, and back to Desmos. All right. Okay, so here we go. So generally here, okay, what we've got, what we end up with up here is this summation, we can approximate that by the natural log of n over k, okay? And then what we have before here, we had k over n, okay? So in our car example, we've got a sample size of 19, and we had a 9 up here, and then we had the log of 19 over 9 down here. Okay, and that would estimate the odds of success for that particular thing. But what we want to do is we want to maximize k. So for a given n, what we'll do here is, let's make a substitution, k over n. We'll just call that x. So, because really we want to know what fraction of n that we want to go with. Okay, for any n, we want to know what fraction. So really it's k over n that we want to maximize. So let's just call it x log x, x log 1 over x. Okay, f of x. This is a function that we want to maximize. Okay, and it's going to end up looking like something like this, and it goes on down there. Okay, so we want to find out what that point is there. So how do we maximize a nice looking function like this? Okay, oh, we're with you. Thank you. Okay. Thanks for the feedback. Actually, it really helps. Okay, and I'm assuming that you can see this. Yes, you can. Okay, so we're going to maximize this baby. So we want the take the derivative thereof. Okay, d by dx of x log 1 over x. And that's going to be equal to the derivative of x times the log of 1 over x plus x times the derivative of 1 over x. Okay, and what's the derivative of x? That ends up being 1. Okay, that was easy. And then times log of x. Okay, plus x times, what's the derivative of the log of 1 over x? Okay, well, I don't know. Let's think of it this way. Let's think of this function as log 1 over x. This just helps out for me. We don't really need to go here, but I think it makes it better for me. Okay, we can treat that as log to the x minus 1, and then we just have negative log of x. Okay, so it's the same function. So let's derivatorize this, and what do we end up with? We end up with negative 1 over x. Okay, copacetic, we're good. On to the next. I think we're pretty quick over there here. I think you guys are getting it. So, hey, let's do this. So we got this. Okay, so what do we got here? We finally end up with all of this becoming equal to the log of x plus the derivative of the negative log of x, which is this. So x minus 1 over x. So really, it's going to be minus the log of x minus 1. Okay, so, and that's the thing that we want to make equal to 0. Okay, so that means that the log of x equals 1. What does that give us for x? X is going to equal e. Isn't that beautiful? So our k, hang on here. I think I messed up here. Call k over n equals x. Somewhere in there, I got a negative sign wrong, because I got what I ended up with here is k over n, which is x, and that equals e. So we've got this fraction ends up being a positive number. Somewhere in here, I got my negatives messed up, and this should have been a negative. Okay, so then x ends up being 1 over e, and I'm doing a little bit of hand waving here because I'm not sure how I did that. Okay, so x ends up being 1 over e. Okay, so that is our optimum right there. We choose 1 over e as our proportion, as our sample size, then that optimizes the chances of choosing the best one. And 1 over e is about equal to 0.368. So you might have even heard, people talk about this. You look at your sample, and you look at the first third of them, and then you throw those out, and then you choose the one following that is better than any of the previous ones that you've already looked at. So, and of course, it's a little bit more than a third, right? So let's say you go, oh, I want to get married in 4 years. Okay, so what I'm going to do here is maybe I'm going to date for 48 months. Okay, and by the end of 48 months, I need to find my future love, my spouse or whatever like that. Okay, so what you're going to do is you're going to take that 48 months and you're going to multiply that by 1 over E. And what do you end up with? What's 48 divided by, well, let's call that 48. Let's call that 48 months. Let's call that a number of days. Hey, so 40, so that's 3 years. So 365 times 4 years. Okay, so that's 1,460 days. So 1 over E months, 1 over E times 1,460 days. Okay, that you've got to find your one true love. All right, so you're going to multiply that by 1 over E. And what do you end up with? Let's see here. $537-ish. Okay. I'm getting stuff popping up here. All right. Okay, so sorry about that. Where are we at here? Okay, so that equals 537, and these are all days. That's days. So what's that divided by 7? Let's work that out into something that we can make sense out of. It's going to be a year and a bit, isn't it? So 537 divided by 7 equals 76.7. So I don't know, let's just say 77. Okay. So that's equal to about 77 weeks. So what you're going to do is you play the field for 77 weeks. Okay. You just kind of see what your options are. Okay. If you're a guy looking for a girl, which is, I think, 99% of my viewers, I check my stats. They're guys anyway. Okay, so you spend 77 weeks seeing what kind of person's out there. Okay, but you don't react. It's been good to know, and then you go on to the next one. Okay, and so then you choose the next best person to come along. Isn't that awesome? I mean, assuming that she chooses you too, I guess you got that to go with, eh? Yeah, I suppose that would rank it. If she thought that you were horrible, that should probably put her lower down on the list of potential spouses. So that's it. That's the love algorithm. Okay, you take whatever sample you've got, you multiply it by 1 over E times your choices, number of choices. Okay, and then you rank them. You rank the first 1 over E, just a little bit more than a third, and then you choose the next one to come along that is better than any of the previous ones that you chose. And that will maximize your happiness, and you will live happily ever after. Actually, it worked out to about a third of the time. Oh my goodness. But I mean, that's just the odds of getting the absolute best. Okay. And you'd probably be happy with number 2. I mean, I happen to end up with best overall because that was me. Okay. But not everybody will. You might have to be happy with number 2. Any questions before we go? Shall I say, remember to thumbs up if you enjoyed that? And Bob's your uncle. Let's just post. I'll post some other links here. And I'll also post a link. I think I've got an article. If I do, I'll post it where I go over this in a little bit more detail. Actually, no, I'm working on one. And when I'm done, it'll be posted. So thanks you all. Thank you, Beryl and Dabixi. You two rock. And we'll talk to you next time. And the idea is that I do this every Sunday at 9 a.m. Pacific. So cheers.